impulse equation, and let's just take a classic example where you might have a ball heading towards a wall, and let's just say it has a mass m and it's moving towards a wall with speed v. So this is the situation before the collision. And then after the collision, let's just suppose it bounces off at the same speed, and so it's a kind of perfect bounce and it heads back the other way at speed v in the opposite direction. So after the collision, we've got that situation. Well, we can apply the impulse equation. Do you remember what it is? The impulse equation is F delta t equals delta p. Well, let's suppose that we want to establish what force acts on the ball during the collision. What force acts on the ball during the collision? So in other words, we can rearrange our impulse equation and we write it as follows. We say, well, okay, so the force is delta p over delta t. We could call that the rate of change of momentum, or the change of momentum over the time taken. So we need to establish what the change in momentum is. Well, the change in momentum is going to be the final momentum minus the initial momentum. Now, before I actually put in the figures there, it's worth just sort of thinking intuitively what you think the answer might be, because it's quite a classic question. You know, what's the change in momentum of a ball when it bounces off a wall at the same speed coming back as it was approaching? A lot of people think, oh, you know, 0 for some reason, but it's not, and you'll see why. Because the final momentum is because momentum's a vector. The final momentum is plus mv if we take momentum velocity to be positive going to the right, and then we have to subtract the initial momentum. Well, the initial momentum will be minus mv, so it's minus mv, and of course that gives us 2mv. So interesting, and so therefore we can write down that the force on the ball due to that collision is going to be delta p 2mv divided by the time taken, delta t. Let's just do it with some numbers, because it always makes life a little bit easier to put in numbers and see what's going on. So we'll repeat the whole thing now with, and let's say the mass, let's say it's going at 2 meters per second towards the wall, and it has a mass of 0.2 kilograms, and then bounces off exactly the same, 2 meters per second, and it has a mass of 0.2 kilograms still, of course. And we can just do the same process. So we say, okay, well, the change in momentum delta p this time is going to be the final momentum, which is 0.2 times 2, m final, v final, 0.2 times 2, minus 0.2 times 2, yeah? So that's the initial momentum. And if we evaluate that, what do we get? Well, we get 0.8, because we've got 0.4 plus 0.4. So we get 0.8 kilograms meters per second. And then when we apply our impulse equation to find the force, well, we need to know the time of the collision. So let's suppose that delta t is let's suppose it was 0.16 seconds. That sounds a bit reasonable, doesn't it, for the time? So that's just the time that the ball is in contact with the wall. That's the time of the collision, not the time for the whole journey. So just be clear that it's only the time of the actual change in momentum occurs, which is during the bounce itself. And so then we can find the force that must have caused that change in momentum. Well, it's delta p over delta t, so it's 0.8 divided by 0.16. And if we knock that in the calc, then we get 5 newtons, exactly, on this occasion. So, interesting, yes? If a ball bounces off a wall, then its change in momentum, at the same speed, its change in momentum is 2 mv. And for this particular example, we can see the force that has to apply over that period of 0.16 seconds in order to change the ball's momentum from 0.4 one way to 0.4 the other way, or from coming towards it at 2 meters per second the force has to decelerate it and accelerate it again the other way, and the force required in that, if it happens in that time of 0.16 seconds, is 5 newtons. So that's what it all means. I hope that gives you an example. So your challenge now is the impulse challenge coming up after this video. So there's a couple of past questions which use this impulse equation. See if you can work out the answers. Have a go.